Hello. In this video, I summarize the research article titled Simulator for Intelligent Workload Managers in Heterogeneous Clusters, which was developed at the University of Cantabria by the Computer Architecture and Technology Research Group. The main idea in this research stems from the fact that managing the workload of a large computer cluster, like a high-performance computer, is a complex task. Designing and testing workload managers can be very time-consuming, especially now that some authors are considering machine learning to solve the problem. For this reason, we have created a workload simulator that allows forecasting the behavior of large clusters in a fraction of the time required by a real execution. In a computer cluster, the workload manager is a piece of software that has the task of allocating computational resources to the jobs submitted by the users. It must decide what job goes to which resource and at what time. This is a hard task, especially if we consider that the users wish their jobs to finish quickly, and we also want to make the most of the cluster's resources. This means that there should be no gaps where resources are idle, and jobs should not be queued for too long. At present, the task of the workload manager is becoming increasingly complex. This is for two reasons. First, the nature of computer clusters is changing. Previously, this used to be composed by similar computers or nodes, but now we are seeing a wide variety of nodes with different speeds and processor configurations with different numbers of cores, or even compute accelerators like GPUs. The second reason is scale. Since the technology is becoming smaller and cheaper, it is possible to pack a larger number of computational resources in one data center. For these reasons, some authors are leaving the traditional programming for the implementation of workload managers and resorting to machine learning techniques. This makes sense because workload management is similar to the job shop scheduling problem, which is NP-hard. And this popular technology has been successfully used to tackle other NP-hard problems. However, machine learning techniques require a training phase that consists on many realizations of the same experiment. If we are considering the execution of hours worth of jobs in a large cluster with hundreds or even thousands of nodes, this training phase will be completely impractical. The conception of a simulator requires considering the level of detail and balance it with the execution time. In this case, we need to simulate thousands of cores during hours or days. The simulator must not be of a very fine detail level because the speedup must be incredibly high. As a consequence, the models of the simulator must focus exclusively on the aspects of reality that are relevant to the workload management problem. But why create another computer simulator? What are the features that we wish we had that are not available in other simulators? First, it's speed. We cannot use processor-level simulators as they are too slow. Second, it's the heterogeneity of the clusters. We wish the simulator to be able to model clusters with a varied hardware. Third, machine learning possibilities. A main drive of the simulator is to experiment with machine learning workload managers. And fourth, the extendability. As an experimentation tool, it is key that new ideas can be tested as painlessly as possible. IrmaSim is what we have developed with these objectives in mind. It's written in Python and takes the advantage of PyTorch for the machine learning functionality. It used to be based on BATSIM, but recently this dependency has been removed. The source code can be found in GitHub, and the installation is straightforward using pip. To run, IrmaSim requires three pieces of information: the platform that defines the cluster in terms of its hierarchical structure and performance of its different components; the job trace, which is a list of jobs that will be submitted to the cluster, with user-supplied details like submission time or internal aspects like instruction count or memory requirements. These can be extracted from a real application with the well-known tool Liquid from the Regionales Rechenzentrum Erlangen in Germany. Finally, the third file has simulation parameters like optimization objectives, policies, or machine learning agent details. From the perspective of simulating user jobs, IrmaSim must forecast the execution times of these jobs. A good start for this is relying on the CPU performance equation using the data from the trace and the platform. However, this equation is insufficient because it does not model the delays derived from memory access, especially when other applications are competing to reach the memory. Therefore, we added a factor to this equation that is the memory speedup. But since this value lies between 0 and 1, it is in fact a slowdown. We will see that it can be estimated based on the number of applications accessing the memory and their access rate. To determine this memory slowdown, we considered all applications to have a steady memory access rate and devised a benchmark that would have this behavior. Then, we studied the performance of the benchmark with different access rates, first alone, and then executing with other instances of the benchmark. Our findings are plotted in this 3D graph, where the horizontal axes are the access rate of the benchmark and the study, and the combined access rate of the other benchmarks. The vertical axis is the slowdown measured in the benchmark and the study. Observe that there are three distinct areas: a high-performance plateau, where the access rate of either the benchmark and the study or the other benchmark is not too high. Then there is a linear performance decline when access rates increase. And finally, there is a saturation valley when the memory access channels cannot handle the demand. Through regression analysis, we were able to fit a piecewise linear function to this behavior. The parameters of these functions are the high-performance plateau, the start point and slope of the linear decline, and the saturation valley value. The parameter A is constant in all situations. B and C depend only on the test machine's architecture, but D required a second regression analysis and was fitted to a smooth step function, which is a smooth version of the piecewise linear function. The parameters of this second regression can be attributed to the test machine and the number of benchmarks running simultaneously. The energy consumption model was also extracted from measurements taken in real machines. This time, after several executions of the NAS parallel benchmarks, we measured the average power consumed by the machine with a growing amount of active cores. Then, we fitted this data to a linear model that depends on two parameters: PB, that gives the idea of the power consumption by the parts of the processor common to all cores, like shared cache or the memory controllers, and PA, related to the consumption of each individual core. To demonstrate the machine learning functionality of IrmaSim, we have developed a workload manager that uses deep reinforcement learning. This relies on the agent making decisions about the next action to take. These actions have an effect on the environment, which in our case is the job queue and the cluster. The effect is conveyed back to the agent together with a reward that judges if the effect has been good or bad. Over time, the agent learns to take actions that bring good rewards and avoids the others. At the beginning of this video, we highlighted the scale of modern computer clusters. As a consequence, the number of actions that can be taken is staggeringly large. Instead of allowing the resource manager to dictate which job goes to what resource, IrmaSim allows it to choose among a set of policy pairs. The first policy chooses a job from the queue, while the second chooses a resource from the cluster. Thus, we can have actions like first high core that sends the first job to the machine with the highest number of cores available, or shortest high G-flops that sends the shortest job to the fastest available resource. Again, due to the scale of modern clusters, the state information could amount to an enormous collection of data, which would be impractical for the agent to process. Therefore, IRMASIM can prepare different observations on the state that reduce the quantity of data sent to the agent, while maintaining important aspects of the state of the cluster and job queue. This is organized in levels. The first sends the memory available on each node. The second adds information about the cores and the running jobs. The third incorporates job queue statistics, and the fourth, the dynamic aspects of the queue. The concept of reward is very useful because it allows defining what objective must the agent optimize. Thus, IRMASIM has a set of reward functions to optimize different metrics like makespan, energy consumption, or energy delay product. New reward functions can be easily added. The validation of IRMASIM is done in 3 experiments. The first 2 test the architectural models in a homogeneous and a heterogeneous cluster. The third tests the machine learning functionality. The validation considers 3 scenarios: a simplistic baseline simulator that does not consider memory contention, IRMASIM, and executions performed in a real cluster. This cluster counts with 16 identical machines with 4 cores each. And by changing the CPU frequencies of the nodes, it can emulate a heterogeneous cluster. The jobs used for the validation come from the NAS parallel benchmark suite. The paradigm chosen is serial programming. Dataset size is C. This meant that the execution times ranged from a few seconds up to 20 minutes, and the memory access rates measured between 1 and 16 gigabytes per second. The metrics considered for the analysis are the makespan to test the performance model and the energy for the energy model. Since the makespan gives the wall clock time from the beginning of the first job to the end of the last, the job traces supplied to IRMASIM submitted all the jobs at the beginning, so once the simulator starts, the queue is never empty until the end. The first experiment compares the 3 scenarios with traces of different size in a homogeneous cluster, both in performance and energy. The graphs show that the results of IRMASIM are much closer to reality than the baseline simulation. The good results of IRMASIM are stable, as the errors are not significantly higher when the 10-hour-long trace is executed. The energy estimation of IRMASIM is slightly pessimistic. A similar experiment was made in a heterogeneous cluster, with machines set at 3 different frequencies. The energy and performance predictions of IRMASIM are also closer to reality than the baseline simulation. For the 2 experiments, the relative error in the makespan is around 5% of the real values, and for energy it is within 10%. To evaluate the machine learning functionality, the following experiment was made. In order to optimize the energy consumption of a cluster, 5 policy pairs were selected, which were given to the baseline and IRMA simulators. These graphs show the evolution of the probability of selecting each pair as the training process advances. At the beginning, all policy pairs have the same probability. The agents learn to choose the policies that bring the best rewards, in this case because the energy consumption is smaller. The agent with the baseline simulator eventually chooses shortest high mem bandwidth, while the agent with IRMASIM reaches much faster the conclusion that first high GFLOPS is better. Which simulator has driven the agent to the correct solution? This graph shows the energy consumption that both simulators obtain with each policy pair. Note that the results for the baseline simulator are very similar, which can be attributed to the simplicity of the models it uses. This explains why the agent takes longer to reach a conclusion, as there is no clear winner. On contrast, the results of IRMASIM have 2 policies that are better than the rest: shortest low power, and the one that it actually chooses, first high GFLOPS. This gives a hint of the advantage of using a more accurate simulator to train machine learning resource managers. To conclude, we have presented IRMASIM, a new open-source cluster simulator capable of modeling heterogeneous clusters with memory contention, and that can also execute machine learning workload managers. And through a set of experiments, we showed that it improves on simpler modeling approaches and compares well to real executions, with errors under 5% and 10% for performance and energy, respectively. IRMASIM is still in development, and new features will come, like modeling contention on input-output or network access, or new policies or agents, or observation and action spaces. We encourage you to download it and try it out, because we believe that it is a great tool to explore the novel field of machine learning resource management.